We now want to look at heterogeneous equilibria. So in this section, well, so far everything that we've looked at has been homogeneous. In other words, everything has been in the same phase. However, we will find that in a heterogeneous mixture, it has more than one phase. The concentrations of the solids and pure liquids are not included in the expression. As an example of this, we've got lead chloride, which is in equilibrium with lead ion and chloride ion. Well, here, since the solid is not in the aqueous phase, we are not going to include it in the equilibrium constant expression. So our equilibrium constant expression for this will not have anything in the denominator, or rather it would have the value of 1 in the denominator. So our concentration of lead ion times the concentration of chloride ion squared would be the value for this. In a similar fashion, we could look at this particular problem where we've got, sometimes it will make it so that we end up with a very simple equation. So here we've got calcium oxide, that is, or calcium carbonate, that is in equilibrium with calcium oxide plus carbon dioxide. Well, you'll notice that both of these are solids, so neither one of them will end up in the expression. And so our equilibrium constant will simply be Kc is equal to the concentration of CO2. Now, we could, if we wanted, write that in terms of Kp, and that would simply be Kp is equal to the partial pressure of CO2. Now, what this means is this allows us to do kind of a cool trick. So here we've got in one of these bell jars calcium oxide and calcium carbonate in these beakers, and that there is some partial pressure of carbon dioxide above that flask. Well, it doesn't matter whether we have a whole lot of the calcium oxide and just a little bit of the calcium carbonate, or conversely, a little bit of the calcium oxide and a whole bunch of the calcium carbonate. We're still going to have the same concentration of carbon dioxide or the same partial pressure of carbon dioxide, if that's how we choose to look at it. So for this, I want to do number 60. And number 60 is kind of a cool problem. We can calculate the value of, we're going to calculate the value of Kc. So let me show you how this one works. All right, so here we've got H2 plus S is in equilibrium with H2S. So at equilibrium, the mixture contains 0.46 grams of H2S and 0.40 grams of H2. We want to write an equilibrium constant expression for this reaction. So here is what our equilibrium constant expression would look like. It would be, and since it is asking for Kc, I am going to put it in terms of concentrations. So we'll have the concentration of H2S divided by the concentration of H2. You'll notice that the concentration of sulfur is not included because it is a solid. So we want to determine what the value for Kc is going to be. So to do that, we need to get the concentration of H2S and the concentration of H2 at equilibrium. So our concentration of H2S is going to be the 0.46 grams of H2S. And we'll divide that by 1.0 liters. And then we're going to also divide by the molar mass of H2S, which comes out to 34.09 grams of H2S per mole of H2S. And that gives us 0.0 0.135 molar. Now, I've written down too many sig figs there, but I'll explain why I do that here in just a moment. For H2, so the concentration of H2 is going to come out to 0.40 grams of H2. Again, it is in 1.0 liters. When we divide by the molar mass of H2, which is 2.02 grams of H2 per mole of H2, that's going to give us a number, which I'll go ahead and write here in just a moment. So I should calculate this just to show you that it's true. So 0.46 divided by 34.09, and you'll see there's the 0.135 that I got in that first part, and then here 0.4 divided by 2.02, and that gives us 0.198 molar. All right, well now our Kc is concentration of H2S over concentration of H2. So 0.0135 molar divided by 0.198. All right, so 0.0135 divided by 0.198. And you can see that we get the number 6.82 times 10 to the negative 3. And we're going to go ahead and round that to 2 sig figs because these really should have been 2 sig figs. So we're going to call that 6.8 times 10 to the negative 2 is our value for Kc. All right. Finally, why can we ignore the amount of sulfur when doing the calculation in part B? Well, because it's a solid. So because it's a solid, it didn't show up in the expression. All right, and that is the end of number 60. So now let's go back to the lecture. The other thing that we want to remember when we're doing this, and this is different than the fact that of homogeneous versus heterogeneous, but if we have a solvent, we don't want to include the solvent in our expression. So we don't want to include the solvent in our expression. So here is an example of a reaction where our solvent is indicated in the equation. So if we take hydrofluoric acid, it does dissociate to a small amount to give us hydronium ion and fluoride ion. And you'll see that we've got H2O included here. Well, we don't want to include the H2O in the expression. So we will write the expression like this, where Kc is equal to hydronium times fluoride divided by HF. So we want to look at number 34, where we write the expression for Kc for the following reactions, and then we also want to indicate whether they are homogeneous or heterogeneous. If they're homogeneous, that means that everything is in the same phase. If they are heterogeneous, that means we have something that is not in the same phase. Usually a solid or a gas will be present. So you'll notice on this first one, we can go ahead and say this one is homogeneous. We've got aqueous, 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 and liquid water. And aqueous means it's dissolved in water. We want to write the expression Kc. So Kc is equal to the concentration of COCl4, 2 minus, and that's to the first power. We don't put water in there because water is the solvent. And then here we'll have CO, H2O, 6, 2 plus. And that one also has a coefficient of 1, so it's to the first power. And then concentration of chloride ion to the fourth power because it is fourth. And since these are all in the same phase, again, we will write this as homogeneous. All right, for this one, you'll see we have solid, aqueous, aqueous, solid. Well, right away, we can write that that is heterogeneous. So heterogeneous. I got a little carried away there. Let's try that again. All right, so heterogeneous. And we will write the equilibrium constant expression, Kc. So our products, we'll put Ag plus squared because of the 2. Zinc we don't put in there because it's solid. And then here we have silver solid, so we don't put that in, but the zinc is in solution in the reactant side. So zinc 2 plus, and that would be our equilibrium constant expression for that. And then finally, here we've got barium sulfate is in equilibrium with barium ion and sulfate ion. Since we have a solid there, we will see that that is going to be heterogeneous. And then Kc is going to be the concentration of barium ion times the concentration of sulfate ion. And since barium sulfate here is a solid, we could put divided by 1, or we could just say that's it. We don't have to put the 1 there since it is implied. So that means that that one doesn't have anything down in the denominator. All right. So next, we want to look at calculating equilibrium concentrations. So we're going to look at the example here. So at 1285 degrees Celsius, we get the following equilibrium established. So bromine, Br2, is in equilibrium with 2Br. And has an equilibrium constant of 1.04 times 10 to the negative 3. By the way, if you look at that, since that is much smaller than 1, we would say that this one is reactant favored. So we should have more of the bromine than we do of the Br at equilibrium. The question is, we have a 0.200 liter vessel, and it contains an equilibrium mixture of the gases. And it had it at 0.245 grams of Br2. What is the mass of Br in the vessel? Okay, well, that's easy enough to do. Easy enough to do. We need to calculate this, calculate the concentration of Br2, and then solve for the concentration of Br. So we know Kc, and we can easily calculate the concentration of Br2. So now we want to calculate the concentration of Br. All right, so there's our question again. And here is our equilibrium constant expression with the value of our equilibrium constant. Here we can calculate the concentration of Br2. We'll just take the mass of the Br2, divide by the volume, and then multiply by the reciprocal of the molar mass. You'll see the grams cancel out, and we will get moles per liter. When we do that, we're going to end up with a concentration of Br2 is equal to 7.67 times 10 to the negative 3. So that will be our concentration of Br2. Well, now that we have that, we can put that back into the equation and solve for the concentration of Br. So if we just cross multiply this equation, we'll get the concentration of Br squared is equal to Kc times the concentration of Br2. If we put the values from over here, our Kc and concentration of Br2, that will give us concentration of Br squared is equal to that product. Well, concentration of Br squared is 7.97 times 10 to the negative 6. All right, if we take the square root of both sides, so here you raise to the 1/2 power, you will get the square root. So we take the square root of both sides, and we will get a concentration of Br that is 2.82 times 10 to the negative 3. So finally, to calculate the mass of Br, we're going to take that concentration of Br, the 2.82 times 10 to the negative 3 molar, which I'm going to write as moles per liter. We'll multiply by the number of liters, and then finally we will multiply by the molar mass. You'll see that the liters cancel out and the moles cancel out, and then that's going to give us our mass of Br. And so our mass of Br comes out to 0.0451 grams of Br. All right, well now let's look at number 39 and 41. All right, so with number 39 and 41, we'll start with 39. And when we look at this, so here is our setup, 100 degrees Celsius, Kc is 0.078 for this reaction. In an equilibrium mixture of the three gases, the concentration of SO2, Cl2, and SO2 are 0.108 molar and 0.052 molar respectively. And that just means that this goes with that number and that this goes with that number. What is the partial pressure of Cl2 in the equilibrium mixture? Well, to solve this, we're going to have to do this in a couple of steps. So first, let's write the equilibrium constant expression. So Kc is equal to the concentration of SO2 times the concentration of Cl2 divided by the concentration of SO2Cl2. And we know that that is equal to 0.078. So that's our value for the Kc. All right. Well, if we solve that equation for the concentration of Cl2, we will get this. So concentration of Cl2, we're going to multiply both sides by a concentration of SO2Cl2 and divide both sides by the concentration of SO2. That's going to give us Kc times the concentration of SO2Cl2 divided by the concentration of SO2. So now we can put the numbers into the equation. So Kc, we decided, or was given as 0.078. Our SO2Cl2 was given as 0.108 molar. And our concentration of SO2 was 0.052 molar. So we'll get 0.078 times 0.108, and then we'll divide that by 0.052. And the number that we end up with there is 0.162 molar. Now we only have two sig figs, but I'm going to go ahead and wait till the end to round, as I commonly do. So we'll go ahead and wait till the end to round. We know from Dalton's law of partial pressures that we can write this. So partial pressure of Cl2 is equal to the number of moles of Cl2 divided by the volume times RT. Well, another way we can write that is the partial pressure of Cl2 is the concentration of Cl2 times RT. Well, we just calculated the concentration of Cl2, so I'm going to put that in, and then for R, we will use the gas constant. So we'll have 0.162 moles per liter. R is 0.0821 liter atmospheres per mole Kelvin. And then finally, our temperature is 100 degrees Celsius, but in Kelvin, we're going to make that 373 Kelvin. Oop, I ran out of room there. So 373 Kelvin. We'll see that the Kelvin cancels out, our moles cancels out, and our liters cancels out. So we'll go ahead and do that. So Kelvin cancels out, liters cancels out, moles cancels out. There's our Kelvin. We're going to be left with our answer in atmospheres. So we'll take the 0.162 times 0.0821 times 373. And that's going to give us 4.96 atmospheres. At this point, we're going to bite the bullet and go ahead and round to 2 sig figs. We had 2 sig figs here and here, so this really should have been 2 sig figs. So we'll go ahead and round that to 5.0 atmospheres. And just in case you're wondering, if you had rounded to 2 sig figs here and made it 0.16, you would have gotten 4.9 instead of 5.0 atmospheres. So not a huge difference. Okay, so that is number 39. Now we want to look at number 41. Okay, so with number 41, our goal here, well, let's go ahead and look at the reaction. H2 plus I2 gives us 2HI. We have an equilibrium constant of 55 and 700 Kelvin. All right, so we've got this flask, has the 3 mixtures, and there are 0.056 grams of H2 and 4.36 grams of I2. What is the mass of HI in the flask? So again, here we're given some equilibrium amounts. We are going to need to do a couple of extra calculations, but that's not a big deal. Let's go ahead and write the equilibrium constant expression. So Kc is equal to the concentration of HI squared divided by the concentration of H2 times the concentration of I2. And that's also equal to 55.3 is our value for Kc. All right, so we're trying to find the mass of HI. So we'll need to calculate the concentration of HI and do a similar kind of calculation that we did on the previous problem. So first, let's figure out what the concentration of H2 and I2 are. So the concentration of H2, so we'll take the 0.056 grams of H2, and since it's a 2-liter flask, I'm going to go ahead and divide by the 2.00 liters. We'll divide by the molar mass of H2, and the molar mass of H2 is 2.02 grams of H2 per mole of H2. All right, so let's go ahead and do that calculation. So 0.056 divided by 2, and then we'll divide by 2.02 and we get 0.0139. So 0.0139 molar. Let's do the same thing for I2. And again, I have too many sig figs here, but we'll deal with that at the end. So for I2, our mass is 4.36 grams. Again, we'll divide by the 2.00 liters. And for I2, let's see, 2 times iodine, I got 253.80. So 253.80 grams of I2 per mole of I2. And so that amount is going to come out to 4.36 divided by 2, and then divided by 253.80. And we're going to get, so 8.59 times 10 to the negative 3 molar. Okay. So now doing something similar that we did previously, we're going to solve this equation for HI squared. So in other words, we're just going to cross multiply. So that's equal to Kc times the concentration of H2 times the concentration of I2. And that should be times. So Kc times the concentration of H2 times the concentration of I2. All right, well, Kc is 55.3. H2 was 0.1 or 0.0. I left a 0 out there. Let me fix that. So 0.0139. And then the concentration of 8.59 times 10 to the negative 3. And scoot that over to get it onto the page properly. Okay, and again, that is equal to the concentration of HI squared. So let's go and clear all that. 55.3 times 0.0139 times 8.59 times 10 to the negative 3. And the number that we get there for concentration of HI squared is 660 times 10 to the negative 3. Well, of course, to get HI, we're going to need to take the square root. So we're going to need to take the square root of that quantity. So the square root of 6.60 times 10 to the negative 3. All right, so I'll take the square root of our answer. And I got 8.13. So 8.13 times 10 to the negative 2 molar. So that's our concentration of HI. So finally, we're now going to take that number to get our mass of HI. And our mass of HI, we'll do 8.13 times 10 to the negative 2 moles per liter. We'll multiply by the number of liters, which was 2.00. And then we'll also multiply by the molar mass of HI. And the molar mass of HI I calculated a little earlier, comes out to 127.91 grams per mole. So now when we multiply all that out, I'll do 8.13 second Oh, here, let's try this again. 8.13 times 10 to the negative 2 times 2 times 127.91. And you'll see that the number that we get there is 20.8 grams of HI. Now, there's one thing we need to do to clean all of this up, and that's to go back and look at our significant figures. You'll see here, here we only had 2 significant figures in the mass of H2, which means we really only have 2 sig figs in the concentration of H2. As a consequence, we will find that all of these calculations also really only have 2 significant figures, which means that when we come down here, the best we can say about this is we'd have to round it to 2 sig figs and call it 21 grams of HI. So 21 grams of HI. And that's going to be our best answer to 2 significant figures. All right. Well, we're going to stop this video because we're already about 31 minutes, and we'll pick up on the next slide in the next video.